desligar o meu.
Bom dia.
Bom dia.
Olha, não é Emerson. Não é Emerson.
Tem que deixar mute, né?
Quando a gente estiver falando, você deixa mutado. Ou então você usa um headset, não sei se você tem algum aí. Vamos resolver. Carlinha não vai poder não aparecer?
Eu acho que ela ia se registrar.
Fala do WRE, né? Sim, Bruno, o negócio do stream, é bom a gente começar o quanto antes, porque assim, às vezes dá problema no stream. Eu já vi vários eventos, a galera tipo, vai streamar a live, aí desiste, porque deu algum problema.
Comecei já.
Tá.
Vocês querem testar o meu vídeo, se fica com alguma coisa de...
Testa aí.
Aqueles flips.
Dá play, Emerson, porque o do LM tá meio esquisito.
Eu posso dar play também. Deixa
eu ver se eu acho
aqui no meu deu certo da outra vez.
O vídeo... Eu tô com o negócio aberto e não tá aparecendo. Ou não tô? Tô. Parece que eu vou ter que ir pelo Google.
Enquanto o Emerson vai testando aí o dele, eu boto. Peraí, acho que o meu é o mesmo, galera. Eu vou tirar a música desse vídeo.
Eu abri o vídeo no reprodutor do Windows, só que não aparece a janela, sabe? Acho que tem que ser no outro...
Bem melhor.
The Federal University of Rio Grande do Norte is among the 10 largest universities in
Tá
Brazil.
legal.
Vou botar baixo.
Tá bom.
Founded on June 25th, 1958,
A
it has
gente
a
viu
built
que
area of
descobri
approximately
ontem
300,000
e
square meters, which encompasses the
quem tá
7
transmitindo que
campuses
controla o
spread all
volume.
over the
Tipo,
state.
se eu diminuir o volume aqui, você diminui também para vocês.
Eu descobri ontem da pior forma, né? Porque eu fui
It currently counts more than 43,000 students, divided into approximately 120 undergraduate programs, 90 specialization programs.
Então, assim, pelo menos aqui no meu deu certo, né? Se não der certo no de Emerson, pode ser no meu.
Quando você terminar aí, pronto, eu vou tentar coisar a minha câmera aqui. Tá indo?
Tá indo sim. Tranquilo.
Tá sem áudio.
Tá sem áudio e tá travando, não sei porquê. Você não... tá tipo...
LM.
Tivesse com lag.
Assim.
Você tá com cabo aí, Emerson?
Oi?
Sua conexão é cabo?
Minha conexão é cabo.
Então devia estar legal.
Pois é.
Vá lá naquela opção de acertar o vídeo lá.
Tem aqui.
Tem aquela opção lá, não sei se você fez lá de Optimize for Video.
Não, fiz não.
Faz isso aí que você vai fazer diferença.
Deixa eu... Cadê o e-mail? Rapaz, eu tirei. Tá aqui.
Tem um negócio aqui no stream do YouTube que a gente tem que fazer manualmente, infelizmente. Mas é o preço que se paga pela tecnologia.
Copiar os links?
Não, a gente... É porque eu não fiz o planejamento de todas as lives já, né? Aí eu tenho que mudar a chave de transmissão de uma live. Quando essa aqui termina, aí eu tenho que manualmente terminar ela lá para ela desaparecer, para eu poder reusar a chave. E a gente não tem que mudar nada no webinar, fica só dando play. Vai, Emerson, testei.
Tô otimizando. O áudio
tá vindo tranquilo, mas Ainda tá
The
travando.
Federal University of Rio Grande do Norte is among the
Agora
10
melhorou.
largest
Agora tá bom.
universities in Brazil. Founded on June 25th, 1958, it has a built area of approximately
Otimiza mesmo, né?
300,000
Porque
square meters.
a diferença é
And
gigante.
consists of 7 campuses
Muito bom.
spread all over the state. It currently counts on more than
Quando a pessoa
43,000
quando você mexe pra ver aí a barra, a gente vê tudo e ele também volta o pena do zoom.
90
Aí volta aqui com a
specialization
tarja preta
programs,
ali. Então, se você for dar play, toda vez que você for dar play, você não pode usar o monitor, basicamente. Tem que dar play e deixar
eu tô
lá.
ligado. Tem que dar o play
e esquecer a vida.
e assistir
É.
mesmo, né?
É.
Isso.
Viver o
Exatamente.
momento.
Não tenta fazer nada mais.
Sim, não.
É uma coisa estranha, mas é isso aí, infelizmente.
E o pior é que você
Olha.
coloca pra dar o screen na tela, né? Porque geralmente nos
Mesmo você
outros...
dando na tela, mesmo você dando na aplicação, quer dizer,
Na
né? Que eu
aplicação,
nem boto
isso.
na tela, eu boto na aplicação.
na
Aí
aplicação.
ele usa como se fosse a tela.
É engraçado, porque geralmente nas outras aplicações a pessoa pode fazer o que quiser, desde que não esteja, né, na
É.
Deixa eu
aplicação.
tentar o meu aqui, vamos ver.
approximately 120 undergraduate programs, 90 specialization programs, 70 master's degree programs, and 40 doctoral
Ontem, quando o
programs.
LM fez o
It
play
has
lá
more than
daquele
2,300
vídeo que ele
professors,
tava mostrando
of
pra
which
galera,
more than
que era
1,800
a
have a
apresentação
doctoral degree.
do Joaquim, né? Tava muito bom, assim.
It has
Não
more
teve
than
nenhum problema, não.
1,500 research projects and
Inclusive,
300 community
No
service
seu, LM, não
projects.
fica aparecendo
In
tarja
addition
preta,
to
não.
around
Aparece ali o controle pneu do
5,500
zoom ali em
technical
cima, que eu acho que
administrative
é melhor que a
staff.
tarja preta.
Among the areas of UFRN that stand out, we may mention the Brain Institute,
Mas seja
which
isso.
conducts research in the area of neuroengineering for the
Como é que
treatment
tá?
Of
Tá legal?
vascular diseases, epilepsy,
bom.
and other neurodisorders. The International
Vou
Institute
trabalhar
of Physics, which promotes the exchange of scientific knowledge with the international community in strategic areas. The Center of Petroleum and Renewable
Agora pela manhã não vai ter interação com o YouTube não, né? Porque é só uma palestra.
Eu acho que, na verdade, vai ter muita interação. É hoje que vai ter muito, porque
então
é a
tá
palestra do que é o key speaker, né? Key speaker tem muito mais impacto
Isso.
do que...
Não
do
vai
que
ter
a
agora, na
apresentação.
abertura.
Então na
É,
abertura.
na abertura não. Na abertura não.
Então,
Falando
mas
nisso,
quando começar o palestrante, né? Quando começar o palestrante, eu volto pro YouTube
Isso.
e fico lá dando
Mas é
um
bom ficar
suportezinho.
atento também, ver se não tem. Mas o Bruno vai ajudar você também depois.
Sim.
Bruno e Júlio já vão estar livres, né?
Eu vou estar sem mais ficar aqui, eu vou participar da abertura, mas eu vou ficar... Tem um monte de
Beleza.
coisa acumulada aqui. Mas, de qualquer forma, eu vou ficar aqui. Caso dê algum problema aí entre Bruno e Emerson, eu assumo.
E enquanto eu estiver na abertura, eu não vou conseguir fazer muita coisa, não.
Você e Júlio, né?
Nós dois não, né?
Aliás, o seu áudio está um pouco baixo, não sei se é só para mim.
Eu?
Não, pra mim tá tranquilo. Tá tranquilo.
Eu acho que se eu botar aqui melhora.
Melhorou. E também não tem mais eco, né? Tá bom aí.
Uhum. Tô com esse negócio apertando minhas orelhas agora.
Tá. Era o meu volume que estava baixo, na verdade o volume da galera tá alto, aí eu baixei. E o volume do vídeo também estava alto.
Eu tô usando, Helene, tanto para as aulas, aqueles que fica... Você bota
assim,
aquele e não
né?
fica perto. Né? Não é esse não, é bem pequenininho, né? Parece um ponto daqueles de televisão.
Mas o meu minha orelha não foi feita para esses negócios aí, não. Fabricou minha orelha. Não. A orelha de topogijo.
O da minha esposa... A minha esposa, ela fica com dor de cabeça. Ela não consegue nem usar o headset, nem usar esses assim.
Eu fico também. Por isso
coloca isso aí, dali um pouquinho ele cai.
Vou botar uns adesivos grudando.
O meu o meu headset mesmo de jogar. É confortável demais até, inclusive. É excelente, o microfone é bom.
Realmente eu gosto, mas eu acho trambolho, né? Mas mesmo
Não,
assim,
é um trambolho.
eu acho legal. Eu acho confortável também. Mas, assim, é porque tem gente, por exemplo, ele tá dizendo que fica apertando a cabeça dele. Por mais confortável que seja, o cara sente apertando e com o tempo vai começando a doer a cabeça.
O meu dói a orelha.
Eles chamam isso de clamp. Acho que é clamp o nome.
Clamp, né? Faz sentido.
Esse aperto, né, no ouvido. Aí, pelo menos esse meu é muito baixo. Você quase não sente. Só que ele veda muito bem por causa do próprio... Da espuma, né?
Acolchoamento, né?
Do acolchoamento, exatamente.
Eduardo Todd entrou ali.
Ó, o Igor tá por aqui, ó.
Uma coisa, quando a gente está como participante, o participante não vê os outros participantes. A gente vê o chat, mas não tem...
Não tem como saber quem é panelista nem quem é atendido.
Quem é panelista tem como saber, né? Que dá pra gente ver todos, mas os atendidos eu não vejo.
Eu vou convidar primeiro o professor Rubens, que eu não sei se ele vai conseguir entrar, depois a Carla, depois o Abner, depois o Júlio, depois o Bruno e depois o Paulo Drius. Beleza?
Bruno, você pode colocar podia ter colocado aquele slide lá de REST String aqui, pra galera que foi entrando lá no YouTube e tal.
Por causa do glitch.
Oi?
É por causa do glitch que eu não coloquei.
Ah, tá. Emerson não recebeu não? Bota aí, Emerson.
Emerson pode pôr.
Posso pôr. Só não sei se...
no grupo, Emerson.
Tá, vou pegar. O único problema é que eu não tenho o PowerPoint, mas eu abro aqui no Library e se rodar beleza, tudo bem.
PPTX, talvez você consiga abrir. Não tem muita coisa lá não, então talvez você consiga abrir bem lá no Google Presentation também.
Vou procurar aqui.
Como é que é? Tem que ir lá no... Não é aqui na interface não do Zoom, né? Bom, não vou fazer mais nada agora. Tá perfeito, falta 5 minutos.
Quer dizer, falta 5 minutos.
Deixa quieto.
Não, mas deixa, vai, Emerson aí, que é Emerson que tá fazendo.
Vou tentar.
Emerson vai.
Tô tentando aqui. Certo.
Que é útil basicamente nesse tempo de setup, né? Tipo, se você precisar dar um tempinho aí para o chair fazer uma preparação, ou às vezes um apresentador que está com problema de microfone, você bota aí.
Sim.
Eita. Isso é meu, é?
Pronto.
Tem vários slides aí, um para cada momento. Aí. No caso, para o de hoje, tem a chamada lá para a apresentação, tá, dizendo que a semana é abertura. Esse aí é o primeiro. Essas transições aí eu não coloquei, não.
Ele tá fazendo as transições sozinho. Tá, não, eu sou o que tô fazendo.
Você colocou errado. Esse aí foi o que a Alisson mandou.
Aí foi. Eu baixei o PPTX, talvez sim.
Não, mas eu mandei o PPTX também. Mano.
Ah, tá, olha. No caso...
Carlinha?
É verdade, foi o que a Alisson mandou. Tem que ser o que você mandou então, né, Júlio?
Sim, o que eu mandei é diferente.
Você mandou no organização,
no grupo
né?
da gente mesmo. Tá no WhatsApp da gente. Né?
Então, você mandou no outro grupo, né?
No Organização LARS, isso.
Pronto. Eu procurei, eu peguei no do Natalnet. Falta uns 2 minutos aí.
De qualquer forma, a gente tem que esperar a Carlinha, então, bom ter alguma coisa.
Cadê Dreus?
Ah. Acho que é isso, né, Júlio? Deixa eu só...
Vai passando aí. Agora sim. Esse aí tem. Vai passando aí que tem esse aí do primeiro dia, né? Bota o slide desse do dia de hoje. Que tem a chamada para o... Esse aí. O segundo slide depois desse. Vai passando. Aí. O Eduardo está falando ali, dizendo que não tem poderes para falar.
Já falou isso logo lá no início.
Se você quiser mover ele para panelista, Lima, então os meninos podem dar permissão para ele falar lá no chat.
Alô, Carlinha? Bora?
É o Eduardo, é?
Ah, você tá aí.
O Eduardo.
A Carla tá ali como atendi, ó. Deixa eu promover ela aqui.
Tira ela de atender, bota ela para panelista.
Eu não tô conseguindo. Eu tô sem as opções aqui.
Dreus tá aí também? Paulo Dreus.
Olá, pessoal. Bom dia.
Tranquilo?
Bom dia, Carlos.
Bom dia.
Bom dia, Carlinha.
Eu tô sem...
O Emerson não tá como co-host, Júlio, você sabe por quê?
Eu ia dizer isso.
Deveria ter ficado. Tenta ver se você tem a opção. Eu já tenho colocado. Eu coloquei ele lá ontem. Mas não sei por que não. Tenta ver se você consegue. Menu aí.
Procurei, não.
O Paulo tá lá para atender.
Eu não tenho permissão.
Dá uma olhada, Emerson, lá no e-mail do WTD. Eu vi que tinha recebido lá no e-mail do WTD, o Zoom mandou uma mensagem lá dizendo que você foi promovido a co-host. Talvez você só entre como co-host se entrar por aquele e-mail. Faz isso. Sai do webinar, entra lá na caixa de e-mail
do e-mail, né? Que tá falando.
Exatamente.
Tá, Alternative Host. Beleza.
Provavelmente você só entra
pelo e-mail do Zoom que tem lá, né? Porque eu poderia startar também
Exatamente, mas você não vai startar não. Quem vai startar
não.
Bruno.
Pois Bruno mas eu acho que eu entrei por ele.
Você entrou por ele?
Foi.
Então, deveria ter funcionado.
Deixa eu sair e entrar de novo, né? Vai que, sei lá. Show. Rapidinho. Vamos ver.
E agora? Você está como alternative host ou não?
Tô não. Continuo sem poderes.
Entender como é que usa esse negócio aí. O Zoom também não é tão claro assim em todos os aspectos. Né?
Bom dia, Paulo, tudo bem?
Então, no caso, eu vou ficar só para compartilhar as telas, então.
Sim.
Tá, ok. Aproveitar e colocar o slide aqui.
Bota o slide e fica naquele trabalho também do site. Mas você tem um monitor só, né? Talvez você não consiga ficar na...
Só
Se
tem
botar o slide, ficar focado no slide.
Emerson, o nosso pró-reitor até ontem à noite não tinha certeza se ia poder participar. A gente vai iniciar sem ele. Se ele entrar aí, você coloca ele como panelista, tá certo?
Ah, o Bruno, eu estou sem permissão por enquanto.
Eu estou de olho, consigo ver aqui.
Tá certo. Não sei se ele... Bom, eu passei o link para ele ontem. Beleza. Todo mundo aqui, né? Luiz, Bruno, Júlio, Abner, Carla, Paulo Dreus. Faltou alguns, mas eu acho que está de bom tamanho. Bom dia a todos. Já está no YouTube, Emerson?
Já sim.
Beleza, bom dia a todos. Pessoal que está nos assistindo pelo YouTube e pessoal que está no Zoom como atendentes e como panelistas. A gente está aqui para fazer a abertura do LARS, SBR, WRE e WTDR, que são conferências virtuais que estão ocorrendo no ano de 2020, e a gente vai passar a falar em língua inglesa a partir de agora. Good morning, ladies and gentlemen. We are here for starting the LARS, SBR, RE, and WTDR 2020 virtual conferences. Our conferences are of Latin American scope, and at this time it's happening in Brazil. We are from Natal here, hopefully the next year presential, but this year virtual. These conferences aim at promoting a comprehensive scientific meeting in the area that we call intelligent robotics, bringing together researchers, undergraduate and graduate students of computer science, electrical engineering, mechatronics engineering, computer engineering, and related fields. Unfortunately, this year, our event is happening through technical sessions on the web, including oral or sometimes video presentations of full papers and webinars featuring technical lectures of recognized importance in the area. We are very sorry and offer our most sincere feeling to the families of the more than 160,000 people who died due to COVID-19 in Brazil, and we also extend this to families in Latin America and the world. The LARS and SBR, NWA, RE, and WTDR are in all of the associated events, like the competitions, are the primary scientific and academic meetings of our larger event that brings relevant development in robotics that we call Robotica 2020. It also comprises the LARS, SBR, Latin American Robotics Competition, and Brazilian Robotics Competition, the OBR, that is Brazilian Robotics Olympics, the MNR, that is the National Robotics Fair, besides the LAR, SBR, WRE, and WTDR. In the WTDR, we have the CTDR that happens together, where we will give a prize to the best PhD thesis dissertations in robotics and best MSc test dissertation in robotics too. For the first time, we are happening as a virtual conference, as I said above, and we started yesterday and go up to the 3rd of November. The competitions will go through the Sunday. We are looking forward to seeing you on our sessions. The LARS, WTDR, WRE, and SBR is being organizing this year by UFRN, that's Federal University of Rio Grande do Norte, the State University of Rio Grande do Norte, the FURG, that's University of Rio Grande, and Technological University of Paraná. We have people from all of these universities on the organizing and technical program committee. As a representative of UFRN, I don't know if Professor Rubens Marimbondo is in here. No, I don't think so. So I will share my screen. And first, I would like to put a video representing UFRN. Just a second, please.
The Federal University of Rio Grande do Norte is among the 10 largest universities in Brazil. Founded on June 25th, 1958, it has a built area of approximately 300,000 square meters, which encompasses the 7 campuses spread all over the state. It currently counts on more than 43,000 students, divided into approximately 120 undergraduate programs, 90 specialization programs, 70 master's degree programs, and 40 doctoral programs. It has more than 2,300 professors, of which more than 1,800 have a doctoral degree. It has more than 1,500 research projects and 300 community service projects, in addition to around 5,500 technical administrative staff. Among the areas of UFRN that stand out, we may mention the Brain Institute, which conducts research in the area of neuroengineering for the treatment of vascular diseases, epilepsy, and other neural disorders. The International Institute of Physics, which promotes the exchange of scientific knowledge with the international community in strategic areas. The Center of Petroleum and Renewable Energies, through a partnership with Petrobras, considered one of the largest research polls in the field, providing information for more than 1,000 professionals at undergraduate as well as postgraduate level. The National Institute for Space Research, which develops competencies in science, technology, and innovation through satellites and space technologies for the study of the climate, the weather, and the global environmental changes. The Institute of Tropical Medicine, whose goal is the study of infectious diseases more prevalent in tropical continents such as South America, Africa, and Asia. The Digital Metropolis Institute, which operates in the technical and academic formation through the social and digital inclusion of young people, from the basic education up to the postgraduate studies. The Superintendence of Informatics, responsible for the integrated system of academic activity management, an information technology system which is a reference among the Brazilian universities and also used by the Federal Police of Brazil. The UFRN Music School, which objectives are educate, produce, disseminate knowledge, and make music in order to contribute to human development, promote social justice, democracy, and citizenship. Our school hosts more than 20 musical groups and the UFRN Symphony Orchestra, one of the only university orchestras in the country. The CAENI, a permanent commission constituted by a multidisciplinary group of professionals responsible for the support, the orientation, and the follow-up of the institutional policies of inclusion for students with educational special needs, ensuring equity and accessibility for their full development in all academic actions. The NUPLAN, UFRN's Food and Drug Research Center, which is an official laboratory enabled to produce medicaments for the Brazilian public system health. Among its activities, the NUPLAN also offers academic support to undergraduate and graduate courses, promoting teaching, research, social projects, and technological innovation. The Agora, Institute of Modern Foreign Languages, Literatures, and Cultures, which has as its main objective to offer foreign language courses to UFRN's students, academic and technical staff, as well as proficiency exams in order to make their mobility abroad possible. The Agora Institute can also receive all foreign students and researchers from UFRN's partner institutions in its Portuguese for Foreigners course, free of charge. The external representation of UFRN is a duty of the International and Interinstitutional Relations Office in the area of cooperation and student and professor exchange, as well as of the Distance Learning Office in the academic area, through the provision of non-face-to-face and wide-reaching programs. Among the services provided by UFRN to its academic community are 3 university hospitals, 22 libraries, 3 museums, a digital TV channel, a radio station, a communications agency, a publishing house, a center of art and culture, a childhood education center, a dormitory, and a university restaurant. In the area of sports, the university provides official soccer and training fields, gymnasiums, Olympic and semi-Olympic swimming pools. Therefore, UFRN searches for the excellence and the academic innovation through the formation of qualified professionals and educational actions, committed to the production of knowledge articulated with the social and community integration, developing solutions to the regional, national, and international problems.
Okay. As you see, our university, and together with WERN and the Federal Institute of Rio Grande do Norte, and the UFESA, that is another one, are the Federal University of the Federal Institution of Rio Grande do Norte. And we are very happy being part of it. We would like now going ahead and welcoming you from the UFRN part to invite Professor Carla Fernandes in name of the workshop of Robotics in Education. Professor Carla, please.
Can you hear me?
Yes.
Hi, good morning, everyone. First, I'd like to thank Professor Luis Marcos to invite me to be one of the chairs of WIE 2020. This year is going to be a different kind of event. It's unique for all of us, but I think we're going to make an event to be remembered.
That's it, Carla? Okay.
Yes.
We also want to thank Professor João Fabro from Technical University of Paraná, who is now together with people from Robocup in the LARC event, but he helped a lot, Professor Carla, in the WRE organization. In the next, I invite Professor Anderson Abner from the State University of Rio Grande do Norte, who together with Professor Reinaldo Bianchi is organizing the double TDR.
Hello, everybody. Good morning. Well, the workshop on Master of Science and PhD works in robotics, the WTDR, and the graduate works contest in robotics, the CTDR, are events that the main goal is to divulge or expose graduate works in progress or concluded ones in robotics. In this year, we have 3 works to be presented in WTDR and 8 works to be presented in CTDR sections, being 4 master degree works and 4 PhD degree works. At the end of the CTDR, the best academic work in robotics concluded in Brazilian University will be announced and awarded. The presentations will be held on this Wednesday from 4:30 to 5:30 p.m. and Thursday from 3:30 to 6:10 p.m. We'd like to invite you to watch the sessions and appreciate the works. Also, we'd like to thank the program committee members that helped us reviewing the papers and the collaborators that will judge the works in the contest sections. I wish you a great event. Thank you, Professor Luis Marcos.
Thank you, Julio. Thank you, Bianchi, for the organization of WTDR. In the following, we invite Professor Julio Melo, who is the chair of the executive committee.
Hello, everyone. We met yesterday already. So in this year, Professor Luis Marcos invited me to try to gather technology and find a way to broadcast an event online using some web tools. And we made research as good researchers. And found out that Zoom was a good candidate, and we were actually we are trying to give it a try. Well, still we are learning the controls. I'm sure that most of the professors here that are trying to give lessons in classes in this period of disease and due to COVID, they are already facing the same problems we are here. But we are still learning, and we hope that's going smoothly as it's going to us for all of you. And we are already in advance sorry for any troubles that the use of the tool could do to you. But still, according yesterday, things were very, very nice, and we believe that it's something that we are going to try to build some maybe guidelines and to help other conferences that are that are struggling as much as we did to make it possible. Still, we are well, right now. Actually, I was talking to Bruno, and we just found another comment that can be helpful to us in the next days. And we hope that it's going to be even easier to us to host the conference. But okay, according to all the members, things are going well, and I hope for you it's going well too. And I'm really grateful to be here to help Professor Luis Marcos and all the other members of the committee to help to execute this conference. Thank you, Professor.
Okay, thank you very much, Julio. Without you, we could not go online this year. I have to say many, many thanks. Without you and Bruno, who is our organizing chair, and will talk in the following. Please, Bruno.
Hello, good morning. First of all, I would like to thank Luis Marcos for inviting me to join the LARS SBR 2020 organized committee. I immediately agreed to do this since it would be a great opportunity to serve the Latin American and also the Brazilian robotics community in a different way. That is, by playing a different role than as an author or reviewer, which I usually play. However, when we all committed to organizing LARS SBR 2020, barely we knew what lied ahead of us. The global and unprecedented COVID-19 pandemic. Therefore, the challenges of organizing the largest robotics event in Latin America would be even larger in this uncertain scenario. Well, postponing the event was not considered, so we chose a different strategy, adapting it. After many meetings with the special committee on robotics of the Brazilian Computer Society and the LARS SBR 2020 Tech Program Committee, we began search for tools that could bring a similar experience of attending a regular edition of LARS SBR in person, but in a virtual way. After experiment with some video conference tools, we opted to using the best that technology has to offer nowadays to run our event. Some operational issues aside, the conference is being run smoothly, at least according to our opinion. Of course, we are open to hear from the community. I'd like to conclude by thanking everyone that is publishing work at the event. Without the effort of the authors that have been working from home, far from laboratories and physical robots since March at least, the LARS SBR event would not exist. It would even make sense. Thanks also to the invited speakers, Professors Grupen, which is already with us, I believe, Professor Luc van Gaal, and Professor Marcelo Becker. They all have arranged time in their very busy schedule to give a talk at our event. Thanks to the organizing team, who have been working day and night to make everything happen. And finally, thanks to everyone interacting with us through Zoom, Discord, and YouTube. Thank you.
Okay, thank you, Professor Bruno. In the next, I invite Professor Paulo Druz, who is in name of our Robotics Committee of the Brazilian Computer Society.
So, thank you, Luis. In name of the Special Robotics Commission, the SIR, of the Brazilian Computer Society, the SPC, we would like to say welcome to our attending of the 17th IEEE Latin American Robotics Symposium and the 8th Brazilian Symposium of Robotics, the SBR, including the workshop of robotics in education and the workshop in context of thesis and dissertation. We would like to thank you, the local organization or virtual organization of the UFRN, the YFRN, and the UERN, by the brilliant organization in this uncommon period of COVID pandemic. This virtual event is an important milestone in the scientific conference, allowing everyone to participate without any cost in every place worldwide, with access just to internet, making the state-of-the-art robotics accessible to everyone. It's an important point. However, this happened with losses, such as the face-to-face contact and the network for an in-person event. So thank you everyone, organizers and attending, and enjoying this journey to the robotics world. Thank you, Luis.
Okay, thank you, Paulo, very much for your pronunciation. Would you stop sharing the screen, please? Thanks, so we get back to, in the next, I talk a bit, and I think I would like to invite you again, Paulo, to talk about something that happened last year. Our friend Alberto from Australia, I think you are the best person to talk about him, right? We would like to make an honor to him here.
Okay, let's talk again. Look, yes. So, thank you, Luis, again. We will talk a little bit about our roboticist, Alberto Elvis, that moving forward this year, let's say, in May. And the robotics committee of the SBA and the SBC did a tribute posthumous for him. And I would like to remember this tribute just in few words here about Alberto. So, let's give me, okay. Alberto left a huge legacy of knowledge and pioneering in the field of robotics, contributing to the development of the national institute, such as the Instituto Tecnológico da Aeronáutica, ITA, and the Renato Archer Information Technology Center, which was the director of the extinct Automation Institute. He was also worked in foreign institutions of scientific relevance, like the IBM J. Watson Research Center, the NASA Jet Propulsion Lab, and the Societal Data 61. He will also participate in the United Nations program to the development. Dr. Alberto Elvis developed dozens of research and projects and had more than 140 articles published in the main journals and conferences in the world in the field of robotics, being the author of the pioneering work in the field of mobile robotics when he proposed the occupancy grid. He was the fundamental for the development of robotics. electronic engineering from the Instituto Tecnológico of Aeronáutica in 1975, master in computer science, also from the Technological Institute of Aeronautics in 1980, and doctor in electrical and computer engineering from Carnegie Mellon University in 1989. He was an editor of several international magazines and conferences in the area, and he was also professor visitor from University of Ulm in Germany. Even though most of his academic career have contributed to robotics in foreign institutions, Dr. Alberto Elvis never failed to seek to strengthen robotics in Brazil, have given numerous lectures in Brazil and actively participated in several research projects with national research institutes. Dr. Alberto Elvis was, above all, a great man, described by everyone who know him, like me, as a kind, caring, and friendly person. He will miss all his colleagues, friends, mentors, and admirers of your work. Thus, the society represented here by me gives solidarity to his family. So, thank you, Luis. And thank you to Alberto Elvis by the contribution to our robotics community.
Yeah, we should thank you very much. His algorithms ran inside the spirit that went to Mars, right? So he is such a very good person. Is because some people believe that when we die, we don't die. We keep living in the other plane. And I think it's the case of Alberto. He has done such a huge contribution. We have to say many thanks to him. Okay, I go ahead with our opening ceremony. And all I have to say in regarding to our main track, that is the LARS and SBR, the Latin American Robotics Symposium and Brazilian Robotics Symposium, is that besides the pandemic, we have had about 70, 80 contribution, from which we selected 60. So we are having 60 papers present. Most of them virtually presential. The authors are presenting the papers online, and some of them by video due to problem with connection or due to the author's request. This is good. It's not the best the Brazilian and the Latin American robotics community can do, but we keep the event on and going. By now, I invite you for the next year to be hopefully presential here in Natal for the next version of LARS. And we hope that everything goes smoothly. In this sequence, we are gonna have a talk by Professor Grupen, who is already between us. We thank so much his presence here and for his invitation. By tomorrow, we are going to have the talk by Professor Luc van Gogh from Belgium. We already tested with him and he's up to go with us tomorrow. And from Professor Marcelo Becker, the day after tomorrow. You are invited at 9 to be here again. Today we start at 10, so we have some few minutes yet. We are going to make some tests now with Professor, and so we start after this. So all I have to say is that in name of Federal University of Rio Grande do Norte, State University of Rio Grande do Norte, Federal University of Rio Grande, Technological University of Paraná, we would like to thank all of you for being here. You are the great people who are doing this year event, and we declare our event opened. So we have to say just thank you to everyone, and we'll be back in a few minutes. Many thanks. Julio, Emerson can stop in the YouTube now, right? Bruno wants to
Julio, do you think it's a good idea to stop YouTube streaming?
You know, we have projects here that we don't even know that they are here. Sometimes we just start something and there's someone that's doing this exact same thing and it's even maybe a bit in front of you and you just start from zero, from scratch. And then when you just, we are going to a meeting and then you meet the guy that's working beside you and it's weird. I believe. I don't know. Well, we need to work better on this communication between the inside of the university because we are all researchers and then we're just redoing the work that was previously did by our colleagues. So maybe, but I don't know how to solve it. So we are just going on. Professors, it's almost time. I will stop. I will stop the stream, the splash stream that's on YouTube, and then Bruno, can you resume the broadcast afterwards? Just a second.
And we still have in here Paulo Dreus. Please, Paulo.
I'm trying to mute myself. Yes. Good morning,
How do you do?
Roderic.
Nice to meet you.
Nice to meet you too.
Paulo is the other program committee chair. And we still have also Carla. Please, Carla, are you still there?
No, Carla is not here. I think so, Luis.
Yes, I'm here.
Oh, it's here.
Nice to meet you, Roderic.
I'm not able to see him.
Yeah.
Okay. Now I can
I'm here.
see. Carla.
Carla is organizing the workshop of robotics in education together with another professor from University from Paraná State, Brazil. Julio, I think you met already. He is the guy behind the Zoom.
Mm-hmm.
And who else? I think that is it. And Bruno. Are we alive already? Bruno?
Yes,
we are.
Okay. Is it okay for you, Rod, to start?
Sure.
Nice. So
Should I stop sharing my screen?
It's
Or
on
just
you.
leave it
I
up?
don't. It's on you.
I'll just leave it there then.
Okay. Good morning, everyone. We will start now after our opening ceremony. The talk by Professor Roderic Grupen. This talk is going also through YouTube. You just visit our NatalNet channels and you can follow in there. And we have to say thank you to everyone who is watching right now. About Professor Grupen, he has a PhD in computer science from University of Utah and a master in mechanical engineering. So he combines everything necessary for doing everything. You know, there are other things, but something that is very good for doing robotics. He also has the Bachelor in Physics from Franklin and Marshall College and a BS in Mechanical Engineering from Washington University. Professor Grupen joined the UMass at Amherst in Massachusetts, College of Information and Computer Sciences, currently, right, in 1988, so some time ago. And I have the pleasure to meet Professor Grupen when I was visiting at UMass at his lab, the Laboratory for Perceptual Robotics. He, in fact, is my co-advisor, together with Professor Antonio Oliveira, who is in memoriam right now. And I have to say before starting, many thanks, Rod, for you hosting me there, and for coming here now, for giving us this talk. Professor Grupen does research on embodied intelligent systems and integrating mechanisms, control theory, machine learning, and cognitive processing. He was the co-editor-in-chief of the Robotics and Autonomous Systems journal, and he serves on the editorial board of several other ones. He got some teaching award from University of Massachusetts, and his interests are in autonomous sensory motor systems, developmental robotics, robot learning, mobile manipulation, dexterous mobility and manipulation, robot hands, tactile sensing, cognitive robotics, and embedded control signal interpretation. So I think he will give us a chance on knowing more about him and his labs during the presentation too. And Rod, I have to say again, many thanks for being here. And it's on you right now. Thank you.
Okay. I'm very happy to be here. I'm very happy to meet you all, those of you who I have met. I'm going to try a talk about autonomy. And so this is a subject that goes very far back in my laboratory, well back into the 1990s. Oh, there's a very young picture of Luis. So this is a subject that we didn't know we were studying, but we started studying it when we noticed that we were putting together something that looked like an architecture. And so I should preface my remarks by saying architectures are very risky because you have to build a large, complicated system so that you can realize some aspects of cognitive organization. So bear that in mind when I give the talk. Some of this work goes back into the maybe 1990. But together, the thread goes all the way to today. We're still working on these issues. And so I'm going to try to give you a sense of the best ideas that we've had, and to the degree that we can, how we can implement them on robots. I am sharing this screen now, correct? Okay. So when we talk about autonomy, it really means self-law, which means self-governance and the capacity to make independent, informed decisions. And what I would like to say is that the informed part is very important. Here is a robot from the DARPA Urban Challenge called Jackson, and I would like you to watch what's happening here. A user had driven by teleoperation the robot to walk up to this spot. It was supposed to grasp that valve handle, and it missed. And it didn't stop to think about the state the robot was in. It tried to turn the missing handle, and when it did so, it destabilized itself and fell over. I respect this robot as a very nice piece of equipment, but what it shows is that every roboticist knows this. When you make assumptions about what the robot really knows, we're oftentimes disappointed. Robots don't have much of a cognitive structure yet. And so by autonomy, I think we really need to consider how to build a kind of consciousness in the robot, a kind of common sense, of the ability to reason and plan and predict the future. And in this case, it would have taken just one sensor in the hand of this robot, and he probably would have been able to accommodate the handle and do it correctly and not fall down. The applications of autonomy are wide and large. I've listed some down here on this slide. When autonomy is finally figured out, I believe that there will be a kind of blossoming of the robotics in the human culture, and that we'll start to see them in our grocery stores and at our gas stations, taking care of elderly people, and doing work out in the field for long periods of time where they have to be responsible for their own behavior. There's here. For some reason, my button won't work. Hold on. I'll try this one. Okay. Here's another use case. I'm working on the NASA contract right now. And what they would like is to build some degree of autonomy, bounded autonomy perhaps, into the deep space gateway that is currently starting to fly missions to build an orbital kind of small space station that will orbit the moon and act as a waypoint for exploration deeper into space. In particular, a mission to Mars is in the works shortly after they get the station built. So they will shuttle raw materials up to this position and then make the Mars mission at that site so that they don't have to lift the mass of the spacecraft off the Earth. Instead, it will be assembled in space and then launched from orbit around the moon. It's a very interesting kind of mission plan they have. They will need humans and robots to work together. At times, there will be crew. Many extended periods, they won't have any crew, and the station will be completely autonomous. So what they want to do is to figure out, when people are present, how to maintain the space station, how to do crew habitat and life support. But when the crew is not there, the robot systems have to be able to act essentially autonomously, because there is a round-trip communication delay of on the order of about eight minutes or so. And teleoperation with that kind of time lag just is unsatisfactory in general. And so this is going to be one rather significant, I think, test bed for the science of autonomy. I work mostly on robots right now. Let me talk a little bit about what I think an autonomous system is. I think autonomous systems bear the responsibility for the hazard they produce. They also bear the obligation of being informed so that they do not cause harm to the environment or to themselves. This means that they have to be very conservative, and they have to be intimately aware of what they're uncertain about. And they also need to keep a stored memory about their prior experience so that they can use it again in the future. Experience that can be used to estimate the confidence in the state of the partially observable systems. I have come to believe that every robot is operating, virtually every robot, perhaps not in a manufacturing line, but every robot that we expect to be able to put into the human culture will be operating in a partially observable system, and we must deal with that. They need models to predict what will happen next. They need to be surprised when what happens next isn't what they predicted, and they need to respond accordingly. They need to be able to recover from unpredicted situations and to avoid unrecoverable errors. In order to do that, they have to have a sense of attention, because the world is often too complex and moves too quickly to be equally aware of everything. So that an autonomous robot has to be in control of how they allocate their sensors and motors to the world in order to meet the constraints imposed by the task. In some ways, you could say autonomous systems have to have skin in the game, which is just a way of saying that they have to be invested and have consequences for making mistakes. Much more like human beings and animals than robots have been up until now. So for this talk, what I'd like to do is I'm going to share some of the things that we've been working on, focusing on kinds of where the places that knowledge can be stored in a hierarchical system. It starts implicitly, well, it starts tacitly in the sense that when you build a robot, its morphology and its sensor geometry speaks to its eventual potential as a robot. If you build a Roomba, you'll get a vacuum cleaner. But if you build a robot that can be mobile and manipulate the world around it, then you'll get something more like a primate. And that's our goal, is to think about kind of primate level manipulation and mobility. We're going to work in an area called, that's I think most people call landscape of attractors. It's kind of inspired by the early work of Mark Raybert in his hopping platforms. And I'll try to give you a sense of how that's evolved in our laboratory over the years. It stores implicit knowledge, that is knowledge that is descriptive of skills that the robot has. And so this is not knowledge that can be communicated easily, but it shows up in the behavior and performance of the robot. Explicit knowledge is the new frontier, I believe. While lots of AI systems have thought about predicate logics and various other representations, linguistic representations of knowledge, the Psych project has tried to figure out how much knowledge a robot needs before it can think on its own, and we still don't know. They've been doing it quite a long time. Explicit knowledge in our systems will take the form of what we call an aspect, which I'll define in a few slides, and an aspect transition graph, which is a probabilistic transition representation of the way the means at which a robot can control aspects of its environment. Also, we're going to be talking about the dynamics of belief. And so this is a very important new topic, I think, that's computationally still very challenging. I think it's an open field. We will show you some of our results with an active belief planner, which is just a way to actively control one's uncertainty and give useful and approximate solutions to partially observable Markov decision processes. By the way, if you have any questions, anybody wants to ask questions, I'm not sure what the format we want to use is. But if you do have questions, you can, I suppose, do a chat. And if somebody could watch the chat for me, then interrupt me when necessary. I'd be glad to answer questions. Okay, so implicit knowledge. Quite a long time we've been working on an architecture we call the control basis. This is simply a combinatoric space where we can combine objectives with sensors and motors. And once you define a robot in terms of its physical configuration, that is link lengths and joint angles and joint axes and degrees of freedom in the robot, also the distribution of sensors over that kinematic structure, now you can begin to think about combining sensors as possible references on objective functions for other motor degrees of freedom to descend the gradient of. And so we can always do gradient descent, that is optimize objective functions, many different kinds of objective functions using different combinations of sensors and motors. In essence, everything that's controllable by a given robot morphology is subject to incarnation as an action, and that action can then be used to elicit information from the world. Actions and state descriptions fall directly from this. We use, as the actions, we do a combinatoric construction of objective functions, sensors, and effectors, as I've said. But the state themselves are derived also from the dynamic response of that objective function, of that control action, when it's engaged with the world. And so when you, what this really means is that once you have a robot morphology, that is, the designer of the robot has created a system which then just explores what it can do in the world around it and tries to build kind of behavioral roadmaps in that space. Interestingly enough, I think early in our work, we discovered that if you represent the world this way, you can use logical constraints to prohibit actions. Therefore, you can get some kind of guaranteed performances out of the system. And we did some work on that quite early. In addition, we acquire skills to encode implicit knowledge regarding the aptitudes and the limitations of the embodied system, so that it can do everything it's possible of doing and then learns how to exploit those aptitudes in the world to produce value. This is what that combinatoric basis looks like. This is a construction we call a tracking primitive. The action itself, that's the objective function, phi. This is the sensor resources that you're going to use to establish an error with respect to the objective. And this is the effector resources, the motor and degrees of freedom that you're going to use to try to descend the gradient of the objective function, therefore to optimize the objective function. In this case, sigma expresses concrete facts about the environment. And what we're trying to do is describe facts that are visual, auditory, tactile, any other sensing modality like point clouds that you have in your robot should contribute to an integrated model of the environment around it. And then also to determine what aspects of the environment can we control. The state, as I was talking about before, is just a membership function in the phase portrait over the objective function. So it's the value of the objective function itself and the local gradient in the objective function over many empirical models. I'm going to give you some examples, so I hope that this will become more clear as we go. As I said, it's a somewhat ambitious architectural approach to robotics and the idea of autonomy. The framework was originally designed to be a framework for stochastic exploration over resource combinations, sigma and tau, that establish environmental control affordances. And by control affordances, I just mean stimuli in the environment that the robot can respond to and use to generate motor activity. Convergence events in these phase portraits, that is convergence to a place where phi dot is 0, a fixed point in the potential field, are intrinsically rewarding. And so when you find that you can control something in the world and actually catch the stimuli and regulate its error to nearly 0, then that's an aspect of the world that you can control, and that is intrinsically attractive to the robot, and it wants to practice those kinds of events. Eventually, it's not just one controller, but sequences of controllers and sequences of skills built from other skills. Okay, so here's an example. This is the work, this is quite old. This is work by Jefferson Coelho in my lab in the early 90s. And what it shows is a phase portrait. That's what these panels are down here. And along this direction, we have the value of the potential function. And in this direction, we have the value of its gradient with respect to time, its time derivative. And what we see is that empirically, this is actually from, I think, Jefferson's dissertation. He built them, in fact, empirically by running the robot and modeling how the controllers suppressed error over time. These are schematics of that. They're not real experimental data, but they show you that there's a class of states in the phase portrait that is where phi dot is nearly zero. This model up here, we call it model 0, which is convergence. And all navigation functions, in our framework, we specify that the potential functions, the objective functions, may not have local minima. They must be navigation functions and subject to optimality criteria, so that greedy descent on the potential function gives us optimal solutions. So M0 is convergence. That model 0 means that you're converged, and all controllers, in this case, we have two forms. We have a 2-fingered grasping controller and a 3-fingered grasping controller. Together, they produce 4 different models, M0, M1, M2, M3, and M4. The dynamics of the 3-fingered grasp is different than the dynamics of the 2-fingered grasp. Now, what this allows you to do, if I build a grasping controller, a manipulation controller, I think the M here stands for a moment controller, because what we approached grasping very much as people approach walking. This is related to the 0 moment point of a walking machine. But what we're trying to do is cause a 0 moment by the net contact forces applied to an object. For 2-fingered contacts, you get these 3 models. And if you happen to be in this state right here with high probability, it means you're going to converge to a suboptimal solution. And so one of the things that it allows you to do, which is quite interesting, is to realize, to predict the future and decide that that solution may not be good enough for your task. So you must take action. And the action that Jefferson proposed was to switch to another controller, add a resource, in which case you now are going to navigate along these models in the phase portrait. By proceeding forward on this model, we're going to get to a slightly better solution. But by discarding one of the resources, you actually go to the best solution that the system can get in terms of the lowest error, the lowest coefficient of friction necessary to actually pick this object up with that grasp configuration. And so Jefferson pointed out that he could build these kinds of models for real hands. The Stanford JPL hand, otherwise known as the Salisbury hand, was how he did his thesis. These little fingertips were load cells that could give force information. And he was able to build a set of these controllers that would work on various polygonal shapes, all trained on the same sets of controllers for many, many different objects. I thought it was a kind of a breakthrough approach, and very interesting even today, and very unique as well. One of the earliest forms of integrated learning that we worked on these systems was on this platform. Its name is Thing. It's supposed to be a hand in some sense. And we were originally designing it so that it could walk between robots who could pick it up and do manipulation, then put it back down, and it would run over to the next robot and serve as a kind of journeyman grasper for many different robot systems. This was the work of Manfred Huber, also around the same time as Jefferson Coelho. So it had resource model, it has an embodiment, and so it has aptitudes. The sensor resources are the configuration of the legs. All 4 legs could have angle parameters measured for you. And the configuration of the body could be measured by counting the strides the robot took and integrating the displacement in the X and the Y and the theta direction. It turns out the effector resources are exactly the same. So everywhere there is a proprioceptive sensor, a joint angle sensor, or a inertial system, an IMU kind of system. You could also control those directly. You can control the positions and placements of all 4 legs. And you could also use gates to control the X and the Y and the theta configuration of the body. Control types, we use just the moment control I was talking about before with Jefferson's work, and kinematic conditioning to keep the legs from getting too tangled up in the system. So this is how it proceeded. So we just decided to forget most of the models in the phase portrait and just use the M0 model. And so these systems had a state that was either converged or not converged. That is, someplace in the phase portrait that wasn't in M0 or in M0. And that's a very simple kind of developmental prerequisite for control. We think that this animals do something similar. There are several kinds of organizations to the ways that animals explore degrees of freedom. Proximal to distal, from midline to extreme to exterior periphery, from head to tail. These are all developmental things that infant humans exhibit all the time. My son was in fact tested at UMass, and he was a very striking example of proximal to distal, so he became Baby J and famous in the psychology literature. And there's kinematic conditioning. So these moment controllers will recruit 3 legs at a time, control one of them, and try to optimize or minimize the residual moment in the system. So if you put a positive moment on the object, you would want another contact to put a negative moment on the object so that you could, the residual would be near 0. We also used a kinematic conditioning controller that took all 4 legs and controlled theta in order to improve the kinematic condition of all 4 legs simultaneously. This was very important, and it also led to Manfred Huber's first kind of experimental artifact. If you think about controlling these, there are 13 possible controllers, and they have 2 possible states. So it's like a base 2, 2 to the 13th possible control configurations that you could run. And Manfred once also said you could run 1 or 2 or 3 of them concurrently to do multi-objective control using the pseudo-inverse and null space projections in the pseudo-inverse. He took the 1885 1, 2, and 3-way concurrent control options and applied structure to make them lead to a tractable, small learning problem. The first compression he did was he noticed that we could discard the effectors. It didn't really matter how you optimized the system, as long as you could stabilize a 3-legged stance, and that the robot was essentially just a bunch of tripod stances that cycled through different combinations of legs. So we had only 5 bits of this instead of the 13, only 5. He reduced the 13 to 5 and ended up with 2 to the 5. Okay, so this is a dramatic compression of the latent expressive power of the robot, but appropriate when you're starting to learn the fundamental motor policies that the robot needs to be mobile. This is an example of behavioral logic then. In that predicate space, the ones that represent the status of these controllers and determine whether they're converged or not, right? We could then say, well, we don't want the robot ever to try to lift all its legs off the ground at the same time. There must be, out of the 4 possible tripod stances, 1 of them must be converged at all time. Otherwise, the robot will be lifting a leg that it needs for support and falling. That could lead to an unrecoverable state where you would need a human to come over and turn it over again and put it on its feet. And for autonomous systems, that is a very important metric of performance, because if you're on the space station and the next crew is due to arrive in 3 months, if you fall over on the, or get stuck in a corner or something like that, you have to wait 3 months to have the reset. So this robot will try to protect itself and say that you cannot try to explore randomly any combination of actions which will threaten this disjunction, okay? Kinematic constraints if I can show you what I mean by this, if these are the 4 legs, it means that the center of mass of the robot cannot be on one side of this, on both sides of the arc between the opposing diagonal legs, right? So if it leans onto this tripod, the center of gravity must be inside that triangle. If it leans onto this tripod, that one, the center of mass must be on this side, and it cannot be on both sides at the same time. And so that's simply this logical expression here, okay? As a result of these two kind of neurological correlations, things that we would see in a developing and maturing infant, Manfred Huber managed to reduce the size of the model to simply 32 states and about 157 actions. And you know, if you look at if you do the ratio, you can discover that he had eliminated 99.94% of the expressive power of the original combinatorial space. One might say, why would you do that? Well, the reason you do that is because you can build important fundamental foundational skills in the 0.06% that's left. And here's an example. These are very old, so the video is not very good quality anymore. I don't know why videos get worse over time, but they do. This is the robot learning how to do a rotate in place part of a gate, and it learns it in 11 minutes of online exploration. This is the program the robot wrote. The bit pattern in here talks about the 5 objectives and whether they're converged or not. 1 means converged and 0 means not converged. And that's all the state information the robot needed to figure out how to build a control policy, the central cycle of which is expressed by these 2 and 3 concurrent actions running at the same time. Very interesting to find out what the robot learns by this. It's almost explainable if you know what the potential fields are. Another important feature is the robot would stochastically go off the main cycle while it was learning. So it would just randomly choose to go up to some other state. And because of that, it learned how to get back to the cycle from those surrounding neighboring states. So it was robust. If you bumped it or if you blocked a leg from going to its intended location, it could still recover by changing the gate and accommodating the disturbance and getting back to the gate as soon as possible. Now, Manfred didn't stop there. In the course of his dissertation, this was the first. So he had a set of 3 controllers that he ran first. Those were the moment and kinematic conditioning controllers I spoke about earlier. That was the native control basis and called A0. But at stage 1, he used just the moment residual control and the kinematic conditioning control, and he learned a rotate gate, which he then added to his actions. So this is just a policy, a switching rule, a Q table in reinforcement learning terms for coordinating phi1 and phi2 to cause that rotate I just showed you. And it learned it in 11 minutes, and the performance was about 0.35 radians per action that was executed. That seems very small, but you can see the robot was moving rather quickly. That's because you have to coordinate many actions to do these things. After that, when rotate was added to the action set, the next control context could include it. And so now you could learn how to do something analogous to the human stepping reflex that causes one leg to move after the other and sends a newborn, well, not a newborn, maybe a 10 to 12-month-old infant translating across their environment. It's called the stepping reflex in humans. So Manfred called it the step reflex in the robot too. And it learned in about 3 hours how to accumulate about 1.3 millimeters per action. Seems like a small number, but the robot was actually able to move at about 1/3 of a meter per second. Once we know how to step, we add it to the actions and we go down and build stage 3 levels behavior. And in this case, it was to walk. To walk required that it coordinated step and rotate. And so already the primitives are just supporting roles. They're built into certain forms of control knowledge are built into these 2 policies. And from that point on, the robot prefers to use that embedded knowledge rather than learn it again in a new context. So it built a walking controller that could go in arbitrary directions, turning when necessary and translating when necessary, out of basically step and rotate. The primitives involved were just trying to glue these steps and rotates together so that you could switch back and forth. He called that walk, he added it to the action space, and he ended up with navigate. And in navigate, he was able to solve simple little mazes, all mazes, using the same behavior, which was interesting. As a result, this is, I think, one of the very first kind of developmental sequences illustrated by a robot, by external supervision controlling the availability of the resources and the control actions that could be recruited while trying to learn a new skill, to defeat complexity, to learn efficiently, and then accumulate a hierarchy of increasingly sophisticated skills. But you need to acquire environmental models. So the robot would try to walk up irregular terrain the same way it walked on flat ground. And there was nothing it could really do about that unless it could notice in the control transitions of the system what kind of terrain it was on. And so we started thinking about partially observable systems and belief MDPs. These are, so normally you would do in a reinforcement learning in a Markov decision process, but in partially observable worlds, POMDPs, you can convert them to a MDP essentially by using distributions of belief over the underlying states in the MDP. This is a little, I think, subtle to see the first time, but it's beautiful when you understand what's going on. It is used to generalize the control state concept to account for partially observable systems. And it then therefore has a model that it can build as a weighted population of probabilistic state hypotheses that are used to capture the risk associated with the perceptual uncertainty. So now the robot is able to say, wait a minute, I know how to walk on flat ground, but this terrain is significantly different, and I am not sure how to predict the future anymore. Therefore, the robot must accumulate or acquire additional information until it reaches a level of certainty that will keep it from falling or breaking. So the generative model is proposed that will associate the perceptual uncertainty to information gathering activity, which every animal does every minute of the day. While you're doing even mundane things like, walking to the kitchen in the morning, your brain is making decisions about what to pay attention to, what to recall from memory. Everybody's very familiar with their house after they've lived there for a while, so you can even do it in the dark sometimes. This is all all properties emerging from the possession or the construction of these generative models and using them as surrogates for sensors. That is, background knowledge about the geometry of your house is almost as good when you need to use it as having the original sensors gathering that information for you on the fly. This is the work of another person in our laboratory named Rob Platt. And what you'll see in this diagram is this robot is called Dexter. It's a big, these were whole arm manipulators, and these are Barrett hands. And each one of the fingertips has one of those load cells that Jefferson used as well, this next generation of the robot. And what you see the robot doing here now is trying to do one of those moment control objective functions by controlling 6 parallel kinematic chains that come out here and then branch into 3s on both arms. Each one of these load cells is making little measurements of the surface normal just above the signal to noise, and it can tell when it has a prehensile grasp that's been optimized. Now what happens is that once it gets to this configuration, it's in this graph. The state of this system is not 5 predicates anymore, it's 11. And these 11 predicates speak to how stable the grasp is, what kinematic condition the arms are in, and monitors the system so that it can accomplish these kinds of manipulation tasks in an interesting way. So this was a trajectory. It went over here, came back, and then descended down this tree, ended up in this state right here. It also was allowed to impose constraints, in this case, there must be at least one stable grasp at all times. And so that leads to this configuration. So this is like a waiter carrying a tray, right? It's balancing the object on one hand. And when you put two hands on it, you can do it. And there's a third grasp that has the kind of waiter tray grasp, non-prehensile grasp with the other arm. Those are the three. One of those three must be true at all times, okay? If it's not, then you've dropped the ball. And so we realized right away that Rob had just created this kind of transition diagram of all the controllable states that were consistent with this ball. And so this ball, this graph means this ball. And it doesn't include things like visual. It doesn't include the fact that it's a pink ball. It includes only the manual interactions with the ball. And it uses that as the definition of the ball. That means that once you've gathered and represented this graph in memory, it becomes a sensor in some sense all by itself. Because if it follows these transitions, if I execute this action and go from here to here, that means it might be the pink ball. And by the time I've done this action and that action and this one and this one and this one, I can be quite certain just by the history of that sequence of states in response to the controllers that yes, this is the pink ball. Even if I'm in a dark room and can't see it, it behaves the way the pink ball is supposed to behave under the controlled interactions of the robot. This is the nature of all solutions to MDPs. When the world is partially observable, you can recover the latent or hidden state by doing a history or a sequence of operations. We've had some other examples. I won't be able to show all of these and get through everything, but this was some work we did for NASA with the same robot. This is a cryogenic coupler. It's a coupler on a spacecraft that transmits liquid atmosphere, that is air, liquid air, oxygen. It carries communication and it carries electricity in a big cable. And so the first thing you do when you want to integrate a new module into a lunar habitat or a Martian habitat is you hook it up with this cable and it comes to life, all right? So what you see here is the robot trying to do a sequence to make sure that the assembly, the relationship between the receptacle and the insertion that you can see kind of, it's a bayonet kind of cylinder, and it has a small rifling to it that looks like a screw thread. Once you insert it against a force, you can turn it and it mates all of these atmospheric and electrical and communication signals that need to be delivered to the device. If you've ever seen the movie The Martian with Matt Damon, he uses one of those in the movie. So that was just one of the applications you could get by having a kind of a solution to a partially observable system and trying to control uncertainty at every step. You could guarantee that you were in fact moving closer to having the receptacle, the connector inserted correctly into the receptacle by watching the forces that arose and by looking at the constraints that the two bodies have applied on each other. Now, I'm getting a little bit into partial observability, and I think this might be too simple an explanation, but for those of you who haven't worked in MDPs before, I thought maybe I would show us a kind of a simple example. This, the work that I'm describing is a generalization of SLAM technology. So SLAM is simultaneous localization and modeling, and we do the same thing. It's just that we don't always do localization, we always do modeling. No matter what task we're doing, we're modeling the world in the context of that task. In this situation, we have two corridors in a building, and if I enter this door, it's certain death, and if I enter this door, it's untold riches. And so when I start my robot, I place him in the hallway. Here's my robot. I place it in a hallway where it can see a doorway on its right and the end of the hallway ahead of it. And it so happens that if the robot isn't completely certain about where it is, it could be over here because it has the same doorway on the right and the same hallway ahead of it. The trouble is getting to the untold riches, the treasure in this room over here is very risky if you think you could be over here. So I'm showing these little particle filter kind of state estimates that could account for the current level of sensor feedback. It sees a door in a hallway. It could be here with equal probability as here. But the POMDP requires a history of actions to resolve this ambiguity. And so the robot will proceed up the hallway until it gets to someplace where it's starting to see different data. From this position, it can see this door, and so it knows it's close to it. And so a lot of the particle filter particles end up moving from here to here. And if we proceed with it and it goes up and examines the door, it will condense all of its uncertainty into this location. And it's no longer in this hallway. It now knows with a high degree of certainty that it's in this hallway. And so it can therefore go and complete its task and find the correct room, okay? So when the world is ambiguous, additional histories of actions, interactions with the world can be used to disambiguate. It's a very simple kind of general paradigm for recovering state from a partially observable system. And it has continuous analogs as well. Tauken's theorem in nonlinear dynamics also has the same property. Any state information that was missing in the formulation of the problem can be recovered in the history of interactions. So we're going to do that. And I have to do a few definitions so that you understand what we're trying to do. We define an aspect. It's an old term that comes from computer vision. Normally, it would have an object in the center and a camera that could fly over a Gaussian sphere, just a hemisphere that lays on the table over this object, right? And if you position the camera from various places, you should see different aspects, they called them, of the object. And so an object could be recognized just by building this Gaussian sphere and then describing.
Sorry.
Pardon?
Sorry. Luis, you said we could interrupt you for
please.
Questions, right? We have a question from the YouTube.
Okay.
Professor Roseli Aparecida Francelin Romero asked if does the learning occurs online with the experience or exists a training before to apply the system?
It starts from essentially zero. So it's not learning. We haven't done any learning from demonstration at this point. It's all just stochastic exploration of the robot in order to solve an objective function. Any guarantees in the system have to be guaranteed because of the way you restrict the numbers of actions that are allowed. I hope that answers your question. We would like young infant robots, just like young infant animals, not to die before they grow up. And so there has to be some built-in structure, as there is in human beings, to make them avoid actions which they are not mature enough to master, that they cannot solve, that are too complex to learn at their current stage of development. We try to apply the same kinds of ideas in robots. I hope that answers your question. Whoops, I went backwards.
I think, thanks.
So back to the aspects. So we generalize the aspects. We would like this old vision concept, which was very unique, very elegant, very powerful. We would like to generalize it to other sensor modalities. And so these features are not necessarily visual only. They could be tactile. They could be in point cloud data. But they are required to have a rigid spatial geometry. So this could be the walls and the pictures hanging on the walls in a room that you're very familiar with. Or it could be an object in your hand that you are also very familiar with and started to model. And so this becomes the signature of those environmental contexts. And if you can detect with your sensors a set of features, a subset of these 5 features that have the requisite kind of structure, then you believe that this aspect is the familiar place you already have known about in the past. And that must be where you are now. And you know how to interact with this object because you've done it a lot, right? So an aspect is simply the stationary or important structure that the environment allows us to defeat complexity with. So as soon as we see these, we have a kind of a upper level. We're not just related to the signal anymore, Now we're related to artifacts from the signal that say that certain things are true at the same time. Therefore, this environment I recognize. I can recognize this same place the next time I come to it. We build this rigid structure just by taking all the pairs and making sure that they are the same distance apart as they were in our experience. And if one pair is the same distance apart, it's rather ambiguous. But if you get 3 pairs forming a triangle, a closed kind of kinematic system, you get more and more certain. And if you get all pairs that you can draw from 5 features are matching the structure that you've seen before in the past, now you know, you believe you know with high degree of certainty that this is that environmental context that you've encountered before, earlier. The aspect transition graph is just a probabilistic model of, if I see this aspect and I look 90 degrees to the right, can I predict what I'll see there? Okay, so if it's a lot like the coffee cup example, right? If you see this is possibly a coffee cup, maybe it's a flower pot. But when I turn it 90 degrees, I see a handle emerge. This is a new aspect. It has new features in a rigid body structure with the rest of the cup. And now I know it's my coffee cup. All right. So by interacting with the object, it may be ambiguous in your first set of sensor data. But if you interact with the object and change your perspective on it, touch it, feel it, get a sense of the material, expose the handle, now you know it's not the flower pot. Now you know it's the coffee cup. And so we did this with some special objects we called AR cubes. They're like dice, because what we're really talking about is probabilistically partially observable things, right? So we can control how uncertain and how unobservable these systems are. In particular, you can only see 3 of these faces at the same time, no matter what perspective you take. And so you can build large numbers of objects by putting different labels on each face, and deal with large complicated problems on simple objects. And that's why we did this. So if this is what I see at time 0, let's say, one action will go with 85% certainty to this as the next state. And it looks like a rotation where a 4 rotated up to where the 2 was, and the 6 must have been on the bottom and rotated up to this side. And so it thinks it knows, if I apply to this object 85% of the time, I'm going to get this. But there are other actions too. A second action might be to rotate in a different direction. And with 80% certainty, it will yield this instead. Right? And this got 2 new, this is got 2 new objects, labels on these faces, and preserves the 5. And you can tell the 5 has been rotated 180 degrees in this case. But these outcomes are distributed. They're not deterministic. There is a chance that you could go back to yourself or over to some other state, and you must account for that. That's your uncertainty. If this is the solution to your problem, but this is certain death, as in that other example, you may not be willing to risk 7% chance of certain death, right? So what you'd want to do is do actions on this until you can reduce this probability to nearly 0. Eliminate all the dangerous states and do only those things which will help you solve your task. So to do that, we build forward models. That is, if I'm in state S, right here, which is a distribution over states, because that's the solution to MDPs, and I execute action A sub t, let's say it's the black action, then I will get to state S prime, which in this case might be this state 85% of the time. And so when a robot plays with an object or explores a room for the first time, it's trying to build these models. And with these models, you can do quite powerful things. This leads us to the second type of action in the control basis. Looks like the same kind of action as we saw before. The only difference is sigma is now sigma tilde. This is not a real sensor. This is a probability distribution over the inputs, the commands you should send to your resources tau, the motors, from your current state, so that the tracker that goes with this and uses a real sensor will converge. Okay? So it's a lot like saying, I know there's a door over here because I go through that door every day. So if I want to bring that door into my visual field of view, I should turn my head 90 degrees. Okay? And lo and behold, I see the door I expected, and therefore I'm reassured that I'm in the environment I think I'm in. And the more of those tests I do increases my certainty to some arbitrary level. All right. Steve Hart did this work in my laboratory. That's Steve in this picture. In this diagram, it shows that he's presenting objects to that big multi-armed robot called Dexter that I showed you before. And in that context, he would oftentimes wiggle. Oh, here it is. He would wiggle the object in front of the object and in front of the robot to attract the robot's attention. I've gotten these backwards. This picture should go with this diagram. That's the position where he wiggled the object. And so if you were looking for a motion cue in the big laboratory, otherwise stationary, oftentimes you would find moving objects right there where Steve would present the object to you so that you could reach out and grasp it. In this picture, it goes with this distribution. Sorry for the mistake on the diagram. Highly saturated objects were oftentimes, or maybe these labels are just mixed up, I'm not sure. Highly saturated objects would oftentimes be presented where the motion cue happened. And so when we modeled those, we get a bimodal distribution. The reason for that is this peak is the same as this peak, but there was a window right over to the side here. And so the robot knew that if it needed to cause a highly saturated signal to occur, it could either look for an object that Steve was presenting to it, or it could look out the window and it would find that the world was highly saturated and bright outside. Other things we did also. This is a mobile robot that's searching a room. And if it was searching for a book, this was learning from demonstration, by the way. These probabilistic models are from experience, but this was from observing a human do the same task. So if a human was searching for a book, they would enter the door to the room and go to the bookcases in some order. And so we could identify the places where the human being would dwell and inspect the world and label them. And you can see if it's a book, they look quite different than if it's a tool, a clamp, because the person would enter the room and go to the toolboxes in a sequence of movements. And so this distribution of dwelling states is much different than this. If you watch a human, therefore, come in and start searching for something, you could infer what they were searching for, up to some level of uncertainty, right? Again, by watching the history of observations. All kinds of interesting human-robot behavior could be constructed when we notice that the human is likely to do this, and if they start over here, maybe the robot should start here and go backwards. And if they were searching for the book, chances are the human-robot team would do strictly better than the human alone, just because the robot was going to try to go backwards and cover some ground before the human got there. Very interesting work that was done by Steve early on in his dissertation. This is our U-bot robot, and these are search distributions that we would like to see. I wanted to show you that this is the range of behavior you can get out of these systems. In every case, we're trying to form a grasp where the sum of forces and the sum of moments is 0, which is the common feature of all of the grasps, all the prehensile grasps that we produce. And so the robot knows it wants to touch this side and that side of the object, given that its pose relative to the object is as shown here. But if it grasps it right here in this frame, it will be able to pick the object up and then put it back down without changing its orientation. However, if it goes over here and grasps it on the front edge, as I'm showing there, it will flip. And you will get a characteristic change of the features now available to the vision system of the robot. Also, if it grabs it near the edge facing the robot, it will flip the other direction, flip away from the robot. And so these are now just changing the way the search positions for the hands. And so if you'd like to explore what's on the bottom of the object, you can flip it as in that bottom panel right here. I've lost my mouse. This panel right here, right? So if you immediately want to see what label is on the bottom, this is probably the right action. This one will not show you, and this one will show you what's on the back, right? So now you can start to think about what actions should I select based on the information it exposes. And so you can now start to think about strategically eliminating uncertainty in your concept of what this object is that you're manipulating right now. This is the premise of all solutions to partially observable systems. You don't have to manipulate it. You can actually drive around and look at the other faces. And so here's another action that the robot can use where it thinks that it's safe the entire time, right? It doesn't have to touch this object until it's ready to touch it. And it can eliminate all the uncertainty about the identity of this object as it does so. Okay, so each one of the different perspectives that this robot is taking on this object looks like that Gaussian sphere I was talking about before in the old vision work, but you can complement it with grasping, touching, and manipulation as well. Each of these options varies in its degree of information content and in the cost of the action. And so the robot can reason about how to gather enough information to reduce or eliminate uncertainty at minimum cost. Okay, so this is a hypothetical. This is our laboratory now. This is one of those robots. It's the 7th. This is U-Bot 7. The one you were just looking at was U-Bot 6. U-Bot 7 is new and bigger and more expensive. They always get more expensive for some reason, but I can't stop it. So I would say, for instance, where is my coffee cup, right? And so there's a number of things you can do in this environment to determine where your coffee cup is. And you can see there's one here and there's one here. One of them isn't mine and the other is. And in fact, I think both of them are mine, but for the sake of discussion, assume that one of them isn't. Okay, so I can overlay a sensor that might be visual, non-contact, and it might respond to this scene by producing these little equilibrium points, these little feature spaces that I can localize, and I can start to think about their geometric structure, right? So I can start to say, is this a structure that I recognize? The structure that I'm proposing that we recognize in this one is this triangle, right? Because this triangle represents a coplanar set of points that is about, a meter off the ground, let's say. And so that means that it may very likely be a tabletop system that we're looking at because of the height, the altitude of these points, and the fact that they form a coplanar, horizontal planar facet of the feature space. So for that constellation of features, I think I have narrowed down where my coffee cup might be because with high probability, my coffee cup could be on a table. So I look at one of them, and this in fact is my coffee cup. And I can start now to extract features from it to guarantee that it is my coffee cup, to improve my certainty that this is in fact my coffee cup and not someone else's. So you can parse the scene using geometrical structure in constellations at various spatial scales. And this can serve as goals for oculomotor controls, right? So this is just visual so far because vision is an awesome means of gathering lots of information quickly. But perhaps I have to touch this and find the surface normal as well. Maybe that's more expensive to do visually and I should use my hand and my tactile sensors to do it. In which case, this normal and this normal and this normal over here are all parts of some rigid structure, especially the ones that define Mickey Mouse here. If you see these, that could mean that it's my cup. Along with the color and the visual information, the tactile information can make me more certain. You can also think about maybe using a point cloud and getting green places where the curvature matches certain values. And in that place, so there's a nice curved concave surface in here, and there's a convex surface matching it on the outside of this surface. Together with the visual and the tactile data, I'm starting to become very certain that this is my cup. And I'm not doing a global reconstruction of the object. I'm just looking for robust features that have some invariant geometrical structure. So let's think about these potential functions. Now I'm getting back to the landscape of attractors idea. Here is some state space, Q1 and Q2. It could be X and Y, okay? It's a spatial, a plane in space. And in there, we're looking down on two of these attractors. And so anywhere inside this circle, I'm in the domain of attraction of a potential well whose gradient will lead me to this equilibrium point. Anywhere inside this one, I'm living inside a potential well whose gradient will lead me to this equilibrium point, right? So if I decide to follow the gradient in phi2, I will get here. And I know from experience that these two attractors are related to one another, such that if I get to this equilibrium point, now I can descend the gradient in phi1 and get to this equilibrium point. So the domain of attraction of this system has just been extended to include the entire area, the union of both of them, right? And all you need to know in order to get here from anywhere inside this union is a policy for following this gradient until you converge, and then following this gradient until you converge. So we can, those membership functions we were talking about that had to do with going down the gradient and seeing the reference that you're talking about will show us that phi1, gamma 1 is only asserted when I'm in this area, right? Gamma 2 is only asserted when I'm in this area. Both of them are true when I'm in this little intersection, and none of them are true when I'm outside that area. So now you can start to see that the pattern in this vector, which we called an aspect, this is only a 2-bit aspect, but it's an aspect, it's a very simple one, is a surrogate for the original X and Y space, all right? So if I know that I'm here, I can get to this location. If I know that I'm here, I can get to this location. If I know that I'm here, I can get to this location. Notice the opposite isn't true. I don't know how to get here from everywhere. I only know how to get here from everywhere because of the gradient properties of this system. So if you take a lot of these, you start to be able to go places from any of the equilibria or any of the attractors. And so if you link them together in the way that they allow you to transition between spaces, places in Q1 and Q2, you end up with a graph. And the graph, the nodes are aspects. They're multimodal patterns of co-activated controllers, right? So you're in the domain of attraction of 1, 2, or more of these attractors at the same time, and that defines these green dots. And the edges between them are the following of one of the gradients, right? So this gives you a connectivity. It's kind of a roadmap representation that most people would recognize that do path planning, except it's in this abstract space of controllable transitions in a landscape of attractors. If you have a vector of these things, you can then start to build skills in their sequential structure. So you can start to build an attractor that gets you all the way, let's see, start at this node right here. I can follow this all the way over to here, right? And so there is essentially a sequential combination of attractors in the landscape that can, anytime I know I'm here, I can follow this sequence. It verifies if I do the sequence as it's drawn here, it verifies that, yes, I was in fact here. Even if I was uncertain when I started, by the time I get over here someplace, I'm relatively certain that the sequence corroborates my initial hypothesis, right? So I can get over to here and be certain that I'm there now. So by doing these sequences of actions, you can eliminate uncertainty to an arbitrary degree. The longer the sequence, the more informative it is, and the more confident you are that you are in the state you think you're in. Objects have this kind of rigid structure, and so it will be a great place to think about grasping objects. Mobility in rooms, the rooms have some rigid structure too. There's a doorway here, and there's a blackboard there, and there's a chair and a desk, right? And so if you're not sure you're in that room and somebody turns on the lights, you can do queries, you can do transitions, and you can increase your certainty to any degree that you'd like to, in order not to risk damaging or breaking or getting into an unrecoverable state. So we do an active belief planner. I'm trying to keep track of my time here. I think I'm a little over. Luis, how long should when should I cut it off here?
It's about to you, Rod. The section, we will not have any more activities in the morning. So.
Okay, well, please break in and shut me down when you need to move on. I think I have too much left to get through quickly. I put too many slides in, I think.
You are about 1 hour and 10 minutes now.
Yeah, I have a clock here. I know I'm late. So when you have to cut me down, please do.
Okay.
So we built a little planner here, and all it does, this is a dynamic Bayes net. It takes observations, it finds aspects, it interprets sequences of these observations to become certain about aspects, those aspects I was talking about before that have some rigid structure to them. And those aspects then are generated by object hypotheses. And so if I take observations here, I can update the posteriors over the aspects, and I can update the posteriors over the objects. And then an action will cause a transition from this hierarchical state. We call this state right here, but in fact, I start to learn what object I'm dealing with. I can take an action and I can transition to a new state. And so the planner does that, and it simulates the DBN, and it makes predictions about where it should be going in order to improve its state of knowledge about the environment. And then it just keeps doing it. It's very much like a hierarchical common filter. And then each one of these has an aspect transition graph that's associated with each object. And so we can start to think about how to condense belief either over aspects or over objects. And once we know an object, that could be a room or an object that you want to manipulate. When you're certain you know what that is, now you can avoid catastrophic states and try to get to the goal. I'll go through this rather quickly. This is our architecture. That's the landscape of attractors. This is a state, and that is a state. If I happen to be in this state right now, and I know, and I accumulate belief in aspects and in objects, I can pass the belief in objects over to get myself an aspect transition graph and use that to roll out future states in the planner. And so it might say, well, I go this far, it's approximate because we do this in a depth limited search. When I get down to this node, I select that as A star and I apply it to the system. And that A star might get me from there to there, okay? If I'm certain about the room I'm in. If not, it will inform me how, where I am actually right now and where I might actually end up if I execute that action. We apply that to the robot and we take observations back. As I said before, if your balance controller is reaching a stability criteria, a boundary where it might fall over, we can go and eliminate that action from that root node, right? So we can just basically say, you may not explore that entire half of the tree, which I've lost. This entire half of the tree is inaccessible because you could fall down and break yourself if you go that way, right? You can also, for instance, consider other constraints, like maybe your grasp is likely to fail if you move your arm in that fashion, so you can get rid of another one. And so you keep doing this, just like Manfred Huber did. Maybe I have an elevated probability of a collision that I don't want to happen, so I get rid of that. So you can see that you can actually eliminate much of the complexity of this search just by asserting these kinds of constraints on the way. Now I'm going to, I'll show you this one. This is a movie, maybe I can run it a little fast. This object and this object, this object and this object are indistinguishable. They visually look exactly the same. This object and this object look different. This one's distinguished because it has an eccentric mass inside. It weighs more on one side than it does on the other. The rest of them are not. So the robot takes a scene, isolates these three objects, makes a probability distribution over all the objects it knows from the first impression, and then it starts changing its perspective on the scene, and as it does so, updates the posteriors of all of these distributions. So no longer can these objects describe what the robot has seen on the third hypothesis, right? And after a couple of objects, a couple of observations, in this case 5, the robot says, well, just looking at it from different directions isn't going to work, so it starts manually interacting with the objects. And you can see every time it does an action like that, the consequences, the outcome states of the action eliminate uncertainty in these distributions. There it goes. That's the blue one, right? This is purple, I think. So it navigates over to it, looks at it from a direction, eliminates some uncertainty, and then decides to see what's on the bottom. And because that's an optimal next action that gets rid of as much entropy in these distributions as it can. So it keeps doing that for a while. And it uses pushing actions and flipping actions and orbiting and looking from different directions. I think it'll do a push here just in case, maybe. Yeah, so it pushes it because pushing an object like that will cause different outcomes if the object is weighted funny, if it's weighted on one side or the other. Then it flips it again. And you can see it's after about 16 actions, it basically knows the identity of all three of these objects. So this is the kind of uncertainty elimination, the condensation of belief in the identity of the object that might have been generating this entire history of observation, or in this case, the three objects. I'm running long, so I will abbreviate some of my final remarks. If this is a active belief planner, taking observations from the environment and then rolling out a tree and selecting the optimal action, and then applying it to the environment, its output, this belief distribution here, can also be submitted as observations to the next level up. And if this is the object level ATG that talks about how aspects change when you change your perspective on different objects, this is the one that talks about how two bodies, what observations emerge by virtue of putting two bodies in some relative pose relative to one another, right? So if you put a screw into a threaded hole, it basically locks up all of the degrees of freedom between the two pieces. And if you can sense that, just like the cryogenic coupler I was talking about before, you know that you've gotten the screw into the hole correctly, right? So you can do assembly up here just by looking at the object level, looking at the multi-object level. I will skip to some examples. Let's see if I can skip ahead here. So this is a robot, this is an adversarial agent. So this robot is, oh, let me start here. I got to explain this. This is what the robot is supposed to build. It's supposed to put an object that has these features and that feature in this spatial relationship to those markings on the wall over here. And so it finds objects that fit that description, and it starts placing them relative to the other features. This is all unguided, and that was the adversary. The adversary just came in and disturbed the object, and the robot is now looking and saying, wait a minute, the outcome of my last action is not what I expected it to be. It still has a high level of belief that this is the object it wanted, but the object is not presenting itself correctly. And so this robot will then go redo the task. So this is a nice feature of this. I'm not going to destroy anything in the world. I'm going to keep plugging away. I'm going to keep doing the best I can until I match that original structure that I was supposed to build. Okay, so the robot can always be dissatisfied with its performance and redo, and then go on. When it's happy, it can go on and get the other object and try to place it as well. Notice the robot's putting its hand down. That's because it's a balancer, and so it rocks a little. And if it wants good, precise information, it can stop rocking by putting its hand on the floor. These are all emergent properties of the active belief planner that is both trying to solve a problem and accumulate the information necessary to avoid danger. Simple little stack here again. I'm not sure what this one's going to show. I can't remember. Oh, it's unhappy. Let's leap ahead. It's unhappy with the placement of the second object. It thinks it can do better. Its stochastic actions say that if it tries to place that object again, it will be more precise than the first placement. And so it just keeps doing it, knowing it's like a Monte Carlo sampling of its action, trying to make sure it's as accurate as possible. Simple little things like three object assemblies can be built as well, all right? And it can just go say, it knows these positions and it's going to try to put these objects in the same place relative to these that the demonstrator demonstrated. And I'll go ahead because I'm running late. This one is the most interesting and it's the last example. So I'll conclude after this. These two objects are eccentrically loaded. The masses are on one edge. So located right here and located right here. And it can figure that out by interacting with the object as I've shown you before. The other object is not eccentrically loaded and it's supposed to build a T. So it's supposed to put two objects on top of one. And in order to do that, it has to find eccentrically loaded objects and place them. And the assembly level knows that the underlying box will support both of them if their center of gravity is over the surface of the box. These are all things it's learned by exploration, just by trying it. So it will do so. And you can see that it places the second object eccentrically like it's supposed to make the T, and then it goes after the third object and puts it in place as well. So it can actually autonomously do very simple things pretty well, and try to make sure that it doesn't endanger the environment or the task or its own self while it's doing it. And if it is not certain, it can always gather more information. So with that, I'll conclude. And I just wanted to give a shout out to all of the people who have been in my lab over the years. Here's Manfred, here's Jefferson. Will McDonald did the walking platform. There's the grasper. Patrick was the one who built this robot. Steve Hart, Suraj Sen, Dirk Lukin, Mike Flanagan, Takeshi Takahashi, and Tiffany Liu. Of all of these people, only Tiffany is in my lab right now. So thank you very much. And if there are any questions and there's still time, I'd be glad to answer.
Sure.
I'm sorry I went so long. I tend to do that.
That's fine. It's fine. We have the morning for your talk in the program. So I would like to ask if some of our participants have questions, please. We have online at Zoom attendees, and we also have it from YouTube.
I have a question.
Sure.
Sure, Bruno, go ahead, please. So, Professor Grupen, thank you very much for your talk. During your lecture, I was wondering how in this whole architecture do you plug what you actually want or your robots to do, to perform for you, some kind of tasks, some kind of goals? How do you plug this information? For example, in this last videos you showed us some minutes ago, I was wondering, this information, what I want for my robots to do I show them a picture how I want the boxes stacked upon each other, or how this information is passed to the robots?
Okay.
I can do another question later if I have space. So I just going for this now. Thank you.
Yeah, that's a good question, because it's not a traditional kind of XYZ coordinate in space that you want the robot to touch or something. What this robot is and this architecture responds to is knowledge and uncertainty. And so when it was doing the recognition tasks, like the 3-object recognition that it interacted with until it knew the identity of all 3 objects, all it was doing there, all of the goals are essentially information theoretic. So the goal there was to reduce the entropy of the posterior distributions. And it was simply that, the sum of the entropies. And any action that reduced that entropy most was the most effective, most informative action. And most informative actions lead to recognition solutions. So in that case, it was simply the sum of all the entropies in the 3-object posteriors. And it would select the action that reduced it the most because it disambiguated the objects the most. In the assembly problems that we did, it was the KLD, the Kullback-Leibler divergence, between the reference model, and that is a distribution over models that say this is the reference. It looks like it could be built out of 3 different objects on the bottom and 3 different objects on the top. And so it would do that distribution and use that distribution as a goal and try to find objects in the environment and place them correctly so that it generates something closest that it can to the reference distributions. And so this robot always takes information as its task specification. It's a little bit strange to think about tasks that way, but you want the world to turn into the world that you want to see. So you manipulate it until it is, right? That's what is fascinating about this approach, is that it can build things. It can build a stack of boxes in order to get, you know, I'm going back to these chimp experiments that I saw, the Kohler chimpanzees, where you put a chimpanzee in an enclosure and said, get the banana that's hanging way up in the sky there. And you can see the chimpanzees reasoning about this problem. They stack up the boxes or whatever other objects they have in the vicinity until they can get high enough to leap up and get the banana. So they do problem solving by trying to diminish the distance between the banana is in their hand and their current state. And so they use environmental affordances to try to get the difference between those two information states to go to zero. I don't know if that's adequate as an answer. I love to talk more about this, because we're starting to think that that all we really do in order to preserve our survival while we're interacting with the environment is try to avoid dangerous information states and achieve reference information states.
Sure, more than adequate. I think your answer is more than adequate. It completely answered the question. There's two more questions from YouTube, and later, if we don't have any other question, I would like to complement to extend my first question with another.
Okay.
Thank you.
Let me make one, and then I get back to you, Bruno. Rod, where do you classify this research as completely reactive, or can it have some deliberative or previous decision taking? Or is this because it has some model of the goal, and based on this model of the environment, you try to modify the environment to fit this model, right?
Right.
Is this completely reactive, or can you put some deliberative tasks on the top of this? That's
well, it's completely reactive at the moment that the robot is born. I use that analogy, with a grain of salt there, because the robot starts its life without distributions representing objects at all, but everything is uniform, right? And so its ability to predict the future is very bad. Every time it tries to figure out one more layer in the search tree, it just turns whatever it knows into mud after 2 or 3 layers in the search tree, because it just expands everything like a low pass filter, right? So any structure in the distribution just gets flatter and flatter if it doesn't know much about the world. And so at the beginning, the robot doesn't know much about the world and is unable to really think carefully about how to select actions so that it gets where it wants to go. So it has to be very careful to avoid catastrophic outcomes, but everything else is informative, and so it can explore it. But by the time it gets models, it's no longer purely reactive. When the planner tries to roll out several plies in the tree, it's doing it on the basis of some significantly better understanding of the environment. And so if it knows the identity of this object absolutely uncertain, beyond uncertainty, right? So it knows, it's absolutely sure it knows what that object is, then the planner can be very deliberative at that point. But the transition is very smooth and gradual from a complete state of ignorance, wherever all the distributions are uniform, into a complete state of knowledge or certainty, when all of the distributions are 99.99% condensed on some kind of state that it's verified through histories of interaction. So it begins reactive and it ends up deliberative.
So I can say this is an adaptive approach. If you change it to another environment.
Yes, it will. If you change it to a completely new, novel environment, it will try to interact with that environment based on the other kinds of environments it already knows about. You know, so maybe it sees the common structure that it recognizes from some other room it was in, like a door, right? It could try to interact with that door based on experience with other doors. But the placement of the door next to the window could be different and therefore confusing to it. So it doesn't know what this room is, but it recognizes that door. That door, it looks like something it knows about, right? So it transfers relatively well that way, provided that there is a common structure.
Okay. Is there any more questions? If not, I go to you, Bruno.
There's questions from YouTube users, YouTube viewers. There are 3 questions.
Okay.
Can I say it?
You can read it, please,
right.
Bruno.
Petrusio Ricardo, which is from our laboratory, he's just finished his PhD in our lab. He's asking, are features being extracted in the multi-resolution domain? I believe he's referring to the images in which the mud was being recognized.
Oh, good question. Yes, we're using scale space vision and actually scale space signal processors. We're trying to use the same kind of Lindeberg and Kunderink scale space, scale invariant feature transforms like SIFT are based on these scale space features. We've tried to generalize that to temporal scales in tactile data so that, you know, for instance, the texture of a surface that you drag the tactile sensor over could be something that has a particular scale and temporal force domain, right? So you could see a cycle in the texture on the surface that has a characteristic frequency, and that characteristic frequency can be a significant observation and that increases your certainty that you know what the object is, right? Yeah, so we have tried to generate a kind of a universal scale space front end on all of our sensors, both in visual and tactile in the point cloud space that we're allowed to get off this robot. That's the only reason we did that is because that seems to be the best, beyond going to a deep network. Deep networks can actually outperform these systems in some cases, but they also have these kind of pathological problems. So we have resisted going to deep networks at first. One of my graduate students finished doing a grasping and manipulation where he picked up tools and used them on things for NASA based on deep learning techniques, but this otherwise the same, right? So the deep learning techniques just extract features and then do the inferencing for you. But otherwise it's the same architecture.
That was my question. That was my question. You answered it already. Can I take another question from YouTube? Richard is asking, what are the computing requirements for the operation of the robots? Is it all on board, or does it send the sensors data to a more powerful computer?
Yeah, this robot is built to be on board, but it kills its battery life because it's actually the computer which is the most expensive energy sink in the system. The motors can lift up, they can do push-ups all day long, and they won't burn as much energy as the computer that's controlling the push-up. Battery life is quite short if we do it completely untethered. In the experiments that I showed you, you can see there are cables going. Those cables are the compute power has been taken off board. And so we have big host desktop machines that are doing a lot of the kind of active belief planner rollouts and various things like that. And the robot is just getting sent back the commands to the motors. So it is still, I think, beyond our capacity to build a robot that would last more than maybe 20 minutes if it was doing everything on board. And the processors that we have on board probably aren't capable of doing all of the number crunching required. So there's still going to be some expense and some kind of systems engineering necessary to build practical robots that can be completely autonomous. That is unconnected to external co-processing and power.
Sure, that's the goal. True. Professor Josué Ramos is asking, how do you associate your system with behaviorists or a robotic planning architecture?
Behavior-based, you say?
Yes.
Yes. We think behavior, this is all inspired by behavior-based systems. And what we tried to do was get rid of, they used to use subsumption architectures and augmented finite state machines and things like that to combine individual behaviors. And we thought that was beautiful and should be replicated in our system. We just went one step further and said that we're not going to combine them. The subsumption architecture isn't going to be fixed, it's going to be adaptive. And so therefore and also information theoretic. So the partially observable part and the adaptable, if you will, subsumption relationship between controllers is extensions of the subsumption architecture, we believe.
Yeah, I think the core is to use the basis, the function basis, right?
Right, and so the control basis tries to make the robot capable of doing anything it can control. Lots of those combinations are useless and meaningless, right? But it quickly finds those that cause value and utility in the task. And it can construct essentially a subsumption kind of style behavior out of it. So we were very inspired by that early work on subsumption.
And those bases can be used as the subsumption behavior. They can be understandable as behaviors, right?
Yeah, you could probably, when you're finished mastering a task, I would imagine that you could pull out the policy and represent it as a subsumption circuit.
Okay, any more questions? Bruno, you said you had another one?
Yes, it's just a complementary question. I was thinking, is it possible to maybe we could plug some sort of consciousness module into the proposed architecture in such a way that this consciousness would somehow interfere or drive or be the part of information theory that supplies the other modules of the architecture?
Yeah, I don't think I understand what consciousness is yet. But I do like some of the attributes of this kind of a style architecture because of the fact that the robot is very much aware of valuable paths, valuable strategies to follow that make the task closer to the best estimate it has at any particular time. And you can layer them hierarchically. So you can get all the way up to language, for instance. We're hoping, somebody in my laboratory is working on that right now, where the language is just like the highest level kind of internal monologue that the robot keeps about the state of the world. So if all of the lights went out and its sensors went dead, it could still proceed for a while based on the certainty of its prior estimates, right? Just like a common filter. But at the highest level, you could say, I'm in this building, I'm in this room, and I'm sitting next to this table, right? And if all the sensors went dead at that moment, it would still believe that was true and it could carry on. Moreover, it would also know that if I move my arm over here, I'm going to break something. And if I go over there, I'm going to ruin my tactile sensor or hurt a person, right? Because these are all assertions that it can know about. So if those are prohibited states, as I said in the introduction to the paper, this robot in some sense has some skin in the game because it's risking value and it's risking inappropriate or prohibited states in order to take every action. And if it doesn't have good information, if it doesn't have good sensory feedback, the quality of that information degrades continuously over time, right? So I'm not sure what consciousness really means altogether yet, but the hierarchy is compelling to me because it means that I can get up to an abstract level that stabilizes my relationship to the world and allows me to be more and more deliberative, is worried about hurting myself, is worried about hurting the robot's environment. And this seems, in my limited understanding of what consciousness might be, to be heading in the right direction for that kind of a question. But I'm not sure how to answer that question yet.
I think nobody knows that. We have another question from Elio Azevedo on the Q&A. In your DARP challenge example, can your architecture be directly applied to open the valve? If so, what is the sequence of steps for this type of behavior?
Yeah, so I really admire the people that competed in that competition. We didn't. We couldn't field a robot that was that, complex and well built. We build our own little robots, and they're much more modest. So the point at which the robot ignored the sense of its hand on the valve could easily be addressed this way, right? So that if you were to say, well, if I've missed the valve and I don't look at my hand, then one of the outcome states could be I fall on my head, right? And on the other hand, if I do the test and I say, yes, I've closed my hand and I feel a reactive load in my hand, I think that's the valve. If I look in that direction and I see a red circle and my hand on it, now I really believe that's the valve. So I should be able to start moving and remain standing. So I don't know exactly what they were doing. I know that they were combining teleoperated control with autonomous control. And it was the handoff that was the problem. It was the teleoperator, presumably, my best guess is the teleoperator drove it up and stopped it and said, go ahead and turn the valve now, when the robot was not in the right position, and the robot just went ballistic and tried to do a motion that was designed to turn the handle. That was the problem, was the handoff between the teleoperator and the autonomous robot. Still, a truly autonomous robot should have noticed that the operator had put it in a bad state because the handle wasn't in its hand and it didn't see the red circle, right? So if our system, if I were to guess, our system would not risk that because the outcome was catastrophic. If there weren't humans in the area and that robot was on Mars, whoever sent it there would have just wasted $1 billion, right? So that's pretty catastrophic. And so we would imagine in spatial exploration and things like that, that the robots would be very slow and very deliberate and very certain before they attempted actions that could have risky outcomes. And I guess that's the most I can say about that, is it would have been very nice for that robot just to check the load cells on its hand before it started turning the valve. And it would have saved it that external need for a human to come over and pick it up. I'm sorry, that's kind of an unsatisfactory answer. I don't know how I would do that task from start to finish at this point. I just know how I would have stopped it from falling over when it missed the valve.
Yeah, okay. I would make a question for you. I think we might have some students interested to go in Amherst, as Jefferson, Elisete, and so on did from Brazil. And I would ask to you if is this open, this keeps open, and how people here can, if they can send messages or something to you, if some people are interested from this audience.
Yeah, absolutely. you know, they want to spend a summer or something like that. I will mention that I'm getting close to retirement.
Ah,
and I have always wanted to start a company with these little robots that we've been making and sell them along with an architecture for doing this kind of thing. And so I may not be around for 5 more years, but I'll be around for 2 or 3 more years. And if anybody would like to come up and study for a summer or something once the pandemic is over, I would be glad to host them. So yes, you can tell them to contact me directly and we can start the discussion about that.
okay. Any more questions? So I have a final words to thank you very much. It was a pretty interesting talk because this is different from everything that people do around the world. This behavior-based and reactive stuff, people doesn't like it. Mainly the mathematical stuff, that the statistics that is behind this. I think when we talk about math, people get a little afraid. So Rod, I have to say many thanks, and that for sure, I think you are going to have some people contacting in the near future. And if you want to say some final words, please.
I want to thank you all for inviting me to do this. I really enjoyed it. I really enjoyed meeting old friends again. I look forward to actually meeting you face to face someday soon. I think this the symposium that you're organizing is a great contribution to the world's roboticists. So thank you again.
Okay, so thank you. And we are finished with the plenary given by Roderic Grupen. In the afternoon, we will be back at 2 p.m. for the paper sessions. If you want to watch someone, Rod, I think I sent to you the program. And
yes.
You can distribute to our students also if they want to watch.
Okay. Okay. Thank you very much.
Thank you. Bruno, we are over. Thank you.
Okay, so we're back 2 p.m. or something like this. Actually, 2 p.m.
At 2 p.m.
We're going back. I'm going to leave this session open for if anyone can stay here.
Let me call Luciane here, Rod. She wants to see you.